Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will discuss about the refrigerants which are used in refrigeration systems. In this lecture we will cover the definition of refrigerants, how the nomenclature of refrigerants is done, classification of refrigerants and selection of refrigerants. Regarding the definition of refrigerant, the refrigerant is a medium of heat transfer through phase change during the process of refrigeration with some exceptions where sensible energy transfer takes place. There are many substances which are used in refrigeration system for energy transfer process. So, mostly refrigerants are those fluids which are used in a refrigeration system and heat transfer takes place through the phase change. As you can see in a PV diagram, mostly heat transfer takes place during phase change of refrigerants, either boiling or condensation. This is pressure. So, 1, 2, 3, 4. Refrigerating effect is attained here and that is due to phase change. During this process also condensation of refrigerants takes place. So, in most of the cases there is a phase change, but there are some exceptions like air refrigeration system. In air refrigeration system, there is no phase change, but the COP of the air refrigeration system is less than 1. However, in this case, the COP is most of the cases it is greater than 3 or between 2 to 3, and it can between 2 to 4. Let us say nowadays it is between 2 to 4, depending upon the pressure in the condenser and pressure in the evaporator. Now, refrigerants are same as blood in our body. If there is no flow of blood in our body, there is no life in the body. Similarly, if there is no flow of refrigerants in a refrigerating system, it means the refrigerating system is dead. So, they are very important constituent of any or very important part of any refrigeration system. You must have observed in my previous lectures also, we have used while expressing the refrigerants, I have used some numbers like R134A or R22 or R407C. I have used this number alphanumeric expressions. I have used this alphanumeric expression in order to write the refrigerants. I have not written their chemical names. In fact, they are chemicals and most of are driven from hydrocarbon driven chemicals. So, in a nomenclature of a refrigerant, there are two parts, prefix and suffix, R134A, R22, R407C. In some of the books, you will find that this is written as HFC134A. This is written CHFC22. So, these refrigerants are also written like this. Now, we can classify refrigerants as prefix and suffix. Prefix of refrigerant, prefix, and another is suffix of refrigerant. Now, prefix we are using R for all refrigerants, that stands for refrigerant, or HFC or SCFC. For example, if I take chlorodifluoromethane is CHClF2. Chlorodifluoromethane has number 22, this is R22 in fact. But for prefix, it is done like this. First of all, we write C, it is carbon. Then carbon is preceded by, in order of appearance, in order of presence of B, C and F. B for bromine, C stands for chlorine and F stands for fluorine. So, if the composition, suppose for example this composition has chlorine and fluorine. So, so it will be like this C F, sorry, it will be CF, C for chlorine, F for fluorine. So, first chlorine will appear, then fluorine will appear, then carbon will appear. If it is having H also, this will proceed by H. So, this R22 can also be written, R can be replaced by SCFC. Now, I will take another example like tetrafluoroethane, C2H2F4. Now, C2H2F4 is nothing but R134A. Now, here in order to decide prefix, it has carbon, it does not have chlorine, it has fluorine and it has hydrogen also. So, it is HFC 134A. This is how a prefix of a, in the nomenclature of a refrigerating system is decided. Now, let us come to the suffix, these numbers. These numbers are actually these, most of the refrigerants are derivatives of saturated hydrocarbons or alkanes. So, saturated hydrocarbons are CnH2n plus 2. They are simplest form of hydrocarbons having a single bond, and the carbon is saturated with, all the bonds are saturated with hydrogen, that is why it is called saturated hydrocarbons. Is it saturated because bonds are saturated with hydrogen. Now, in a refrigerant, let us go back to CHClF2. This is R22. We will start with CmHnClPFQ. This is a generalized formula for any refrigerant because, but nowadays chlorine is not there in most of the refrigerants because chlorine damages the ozone layer. Those issues will be addressing later on. So, in this case, if I want to give a nomenclature to this, I will write R m minus 1 n plus 1 F. F is Q, sorry, number of F is Q. So, in this case, m is equal to 1, n is equal to 1 and F is equal to 2. So, this refrigerant is going to be R0, n is equal to 1, so 0, 2 and Q is equal to 2, this is R22. Now, we can take another example also for tetrafluoroethane. So, C2H2F4 tetrafluoroethane. Here m is equal to 2, n is equal to 2 and F is equal to 4. So, while doing the nomenclature, we can write R m minus 1, that is 2 minus 1, n plus 1, n plus 1, that is 2 plus 1 and F is 4. So, R 1, 3, 4. In the this refrigerant R134, there is a subscript A. It means it is an isomer. Isomers are the substances which have same chemical formula, but arrangement of molecules is different. Like, so these compounds or chemical substances, they are known as isomer. So R134A is one of the isomer of tetrafluoroethane. So this is how the nomenclature of refrigerants is done. Now we will take the different classes of refrigerants one by one and we will discuss their nomenclature at the same place. For example, classification of refrigerants. So refrigerants can be classified as primary refrigerants and secondary refrigerants. Primary refrigerants are those refrigerants which are circulated in the system, like R134A or air or ammonia. These refrigerants are circulated in the system, so they are known as primary refrigerants. Often they are in direct contact with the substance on which the refrigerating effect is produced. Now secondary refrigerants are those refrigerants, they pick heat from the substance. Suppose I want to cool water, so secondary refrigerant will take heat from water in a freezer and discharge heat to, this is TL, this is TH, and discharge heat to primary refrigerant through a heat exchanger. So it is a link between a substance and the primary refrigerant. For example, in big buildings, chilled water is circulated for the cooling of large size of buildings where when the load is 800 tons or 1000 tons or 1200 tons, chilled water is circulated in the building. So chilled water acts as a secondary refrigerant. So chilled water picks the heat from the room or different heat sources in the building, and chilled water discharges heat to the primary refrigerant. So that is the function of secondary refrigerant. In some of the applications like ice factories, brine water is also used as a secondary refrigerant. Now halocarbons. Now halocarbons or halogenated carbons we have already discussed. Since halocarbons were proposed to be used as a refrigerant 90 years back, and when these halocarbons, especially chlorofluorocarbons, now they are banned like R12, R11. These refrigerants, they are banned because they damage the ozone layer. They are responsible for the depletion of ozone layer, which is vital for the life of on the earth, and they contribute towards global warming. These refrigerants were banned, but when they were introduced 90 years back, they were supposed to be the excellent refrigerants. I mean, they were colorless, they were non-toxic, non-flammable, non-corrosive, and they were not reacting with any metal. But later on it was discovered that they are damaging the ozone layer and causing the global warming. These refrigerants were discarded. In fact, chlorine present in these refrigerants, this chlorine, C, this chlorine creates problem. So in the ozone layer, so now we have refrigerants which are HFCs, hydrofluorocarbons. Only one refrigerant is there which has chlorine, that is CHFC, that is R22, and this refrigerant is allowed to be used up to 2020. Developing countries are given grace period of 10 years, so we can comfortably go with this up to 2030, beyond which it will not be allowed to use this refrigerant. So most of the nowadays there are consistent effort to find a refrigerant which is eco-friendly. Eco-friendly means there is no damage to the ozone layer, ozone depletion potential is 0, and global warming potential is also 0. Now in halocarbons, we are frequently used nowadays R134A. It is a ozone safe refrigerant, it has 0 ozone depletion potential, but it has global warming potential. So in due course of time, this refrigerant shall also be replaced. In addition to the halocarbons, hydrocarbons can also be used as a refrigerant. Hydrocarbons like methane, ethane, C2H6, propane, C3H8. These hydrocarbons can be used as a refrigerant. The benefit of hydrocarbons is their density is very low. So small amount of charge of hydrocarbons is required in the refrigeration system, and the problem with the hydrocarbons is they are inflammable. So a lot of precautions have to be taken while using hydrocarbons as a refrigerant. Regarding the nomenclature, CH4 is written as R50. Now this is methane, ethane, ethylene. I will take ethylene. Ethylene is C2H4. This is not saturated hydrocarbon. This is not a saturated hydrocarbon, and it is written as R. This is 5, 0, because 0 is added in hydrocarbons, and C2 is 1, and because it is unsaturated, it is 1150. So R1150 is ethylene. Similarly, propylene. Propylene is C3H6. So for propylene, it is going to be, that is 70. You can do it by yourself now, 70 to 1270. 1270 is propylene, and this is ethylene. So they are all product of petroleum, since they are inflammable, so their applications are limited. Now azeotropes. Azeotropes are mixtures, and they are a special type of mixtures. These mixtures have, if two refrigerants, if two chemicals, what are azeotrope? First of all, I will define. If two substances which cannot be separated into components by distillation, and it behaves like a pure substance having properties completely different from constituents. It means if we mix two substances, then normally if there is a mixture, then if we do distillation, then all the constituents of the mixtures will be separated out, or can be separated. But in case of azeotrope, if azeotrope is formed, first of all, azeotrope has one boiling point and freezing point. One boiling point. I mean, it doesn't have to. Boil. It has single boiling point. So it behaves like a pure substance or pure refrigerant. And if you boil this azeotrope, the constituents will not be separated out, and azeotrope is formed. I mean, in any proportion, if you mix two substances, azeotrope will not be formed. So there has to be certain weight by weight composition of the mixture. Only then azeotropes will be formed. So here one example of azeotrope is given, 507A. In this case, you can see it is 50-50 mixture of R125 and R143A. You can see the normal boiling point of R125 is minus 48.09 degrees centigrade. Normal boiling point of R143A is 47.27 degrees centigrade. If they are mixed in 50-50 proportion, we are getting R507A, and normal boiling point is minus 46.74, which is higher than these two. Logically, the boiling point should be the average of these two, but you can see boiling point is higher than these two, and 507A behaves like a pure substance. Now, zeotropic mixture. You must have seen the refrigerants like R407C. Now, any number of refrigerant starting with 4 is zeotropic. Any number starting with 5, like 507A. So this is azeotropic, and zeotropic is the number of, it is 4 series. So the number of the refrigerant will start with 4, and it is called 400. In fact, it is called 400 series, and their number of zeotropes are shown here: 407A, 407B, 407C, 407D, E, and A. Now in the 407, the constituents are same, R32, 125, R134A. Now R32 is difluoromethane. Now I should explain this R32 also. R32, it is difluoromethane CH2F2. So if you write CH2F2 for number for CH2F2, then it is going to be H is 2 plus 1, 3 and 2, R32. And similarly, R145, it is pentafluoroethane, that is C2H5, C2H5, pentafluoroethane. So N minus 1, so it is going to be 2 minus 1, that is 1. This H plus 1, 2, and F5, R25. Now, this is difluoromethane and this is pentafluoroethane, and if you mix them in 50-50 proportion, then you get R410A. Now, R410A is seen a very potential refrigerant in the refrigeration industries, and now most of the systems which are coming in the market, especially VRF systems, they are working on 410A. Now, I will tell you the reason later on. Now, another refrigerant which is popular here is 407C, which has R32, R125 and R134A as well in the proportion of 23, 25 and 52% weight by weight. Problem with the 407C is that it has temperature glide. Now, let us understand what is temperature glide. If boiling of refrigerant is taking place, it has suppose it has two components A and B, then A will start boiling at, suppose we start from the room temperature 20 degrees centigrade, A has boiling point, let us say 60 degrees centigrade, another is having 70 degrees centigrade. So, if we keep on heating this liquid, the moment 600 degrees is reached, this constituents A will start boiling, and this boiling temperature will keep on shifting because A is disappearing from the fluid mixture, and it will end at point V where the boiling temperature is 70 degrees centigrade. So, this change in the temperature from 60 to 70 degree is known as temperature glide. This is known as temperature glide. And these type of mixtures, they do not have any fixed boiling point or condensation point, because by definition of boiling point means the temperature remains constant during the phase change. So, this temperature is known as bubble point, and this temperature is known as dew point, because if you are cooling the vapor, first of all B will condense at 70 degrees centigrade and the temperature will keep on reducing till completely A is condensed completely, and this variation is again known as temperature glide. For the more clarity, I will show you the pH diagram of 407C. You can see this is the saturation line, saturation curve. On y-axis, pressure on a log scale. On x-axis, there is an enthalpy at on a linear scale. There is a thick saturation line. On the left hand side, there are vertical lines, constant temperature line, and constant temperature lines are inclined. They are not horizontal. They are inclined because if you want to maintain the temperature constant, you will have to reduce pressure for the boiling, or during condensation, if you want to maintain temperature constant, you will have to increase the pressure during the condensation. If you want to maintain constant pressure, in that case there is going to be change in temperature. So, if you want to maintain constant pressure in condenser or evaporator, there is going to be change in the pressure. Rest of the things in this chart are same as in the case of 134A. That is why these are the selected properties from the properties chart of 407C. You can see here, this chart is based on pressure, it is not based on temperature. If you look at the chart of 134A, it is based on temperature. So, this is a temperature based chart, pressure based chart, and at atmospheric pressure, this is bubble point and this is dew point. It means at atmospheric pressure, the refrigerant, the bubbles will form in the mixture as minus 43.63, and bubble formation or all the liquid will be converted into the vapor at minus 36.63 degrees centigrade. And from here itself, you can see there is a change in the temperature of 7 degrees centigrade. So, the 7 degrees centigrade is the temperature glide in this case, and if you look throughout this property diagram up to 2 bar pressure, the temperature glide is of the order of 7 degrees, not 70 degrees, 7 degrees centigrade. So, that creates problem during operation of the system also, or designing also become typical. But however, in the case of 410A, it is also a mixture, but temperature glide is of the order of 0.1 degree centigrade. So it is near azeotrope. I mean the temperature glide in 410A is it is high pressure refrigerant. The pressure, so normal boiling point of 410A is order of minus 51, approximately minus 51 degrees centigrade. But so the system has to be robust in order to run a system which works on 410A. But in this refrigerant, because the temperature glide is of the order of 0.1 or 0.2, so it is near azeotropic and it is easy to deal with this refrigerant. Now inorganic compounds like ammonia. Ammonia is also used as a refrigerant, and inorganic compounds are covered under 700 series, and nomenclature for inorganic compounds is very easy. I mean you start with, for example, ammonia. Ammonia atomic weight is 17, so it is R717. Water, H2O, atomic weight is 18, R718. Air you can take air, R729, and so on. Helium, argon, R740, argon. So this is how the nomenclature of organic compounds are used. Nowadays organic compounds are becoming popular because throughout the world scientists are trying to go for natural refrigerants. So inorganic use of inorganic compounds is intended to be increased in near future. We are looking for more inorganic compounds to replace the existing chemicals in the refrigeration industry. Now selection of refrigerants. For selection of refrigerants, the focus has to be on the thermodynamic requirement of the system or thermodynamic requirement of the refrigerants, chemical requirement and physical requirements. So these requirements we will discuss in subsequent lecture, which is also on refrigerants.